Hello, everybody. My name is Diksha Karapurkar, and I will be your instructor for this course, that is GIS for Research, Applied GIS for Academic and Scientific Research. This is an intermediate level course, which means that those of us who have not dealt with beginners' understanding of GIS are given access to our 1 month long GIS camp. So, whenever you register for this, you will also receive a link to our GIS camp so that you will be able to develop your understanding about different basic functionalities of GIS, and then you can switch to this particular course, which is an intermediate level. We will also time and again instruct as to for which session you will require which GIS camp sessions to follow up with. With that, let's begin. This is a 4 week self paced online course and is designed for students, researchers, and early professionals who want to integrate Geographic Information System, that we call GIS, into their research workflow. This course is starting from November 10, 2025. The course will take you through the complete process of using ArcGIS desktop and QGIS desktop, from preparing and analyzing spatial data to visualizing and presenting your findings effectively. You will follow a structured learning format with 3 sessions per week, each about 45 minutes. The content will be released weekly, giving you flexibility so that you can learn at your own pace while maintaining steady progress. The course is highly practical. Each week includes hands on exercises and assignments designed to help you apply what you learn right away. By the final week, you will complete a capstone research project. We will be giving you a list of research ideas that you will be working upon in the last week, where you will use GIS to address the real world research questions. And mind that the list will be given by us to you. However, you may as well prefer to choose your own research question. So, upon successful completion of all weekly assignments, you will be awarded with a certificate of completion. Um, our certificate is also ISO certified. We are Pravinya is also ISO certified, which means that this certificate brings a huge credibility to your skill base and uh, to your portfolio, which also recognizes your ability to be able to apply GIS methods in academic and applied research. So, whether your background is in environmental studies, geography, social sciences, or engineering, this course will help you use GIS not just as a mapping tool, but as a research framework, so that you will be able to explore complex spatial problems. Registrations are now open, and since it's a self paced course, you can begin as soon as the course launches. Um, let's let's discuss how GIS can empower your research and expand your analytical horizons through this particular course, which is a 4 week course. I look forward to seeing you inside the course. The first session is open, um, which will be a demo class for you all, and then you may decide whether you wish to go ahead with this particular class. This is the brochure of our camp. uh, the course will be recorded from 10th of November all the way into December, and will be available for registration all around the year. Let us start with our first session. The first session is covering the first initial parts of Module 1, where we discuss GIS for research, Geographic Information System for research. Here we discuss essentially four objectives: the role of GIS in scientific and applied research, research questions that GIS can answer, overview of ArcGIS desktop as a research tool, and framing a research project with spatial data. This is where your foundation for um, taking up your capstone project in the fourth week will also begin. So with respect to that, understand and go through all the sessions until then, and develop your concepts, your methodologies that you will be utilizing, employing during your capstone project in the fourth week. So we will start. Today we are discussing role of Geographic Information System, which is also simply called GIS, in research. We essentially focus on use of GIS in context to research in environmental sciences, earth sciences, ecology, and atmospheric sciences. This is one of those technologies that quietly work behind scenes. Techn- these are the technologies that shape our world, the world that we live in, yet most people don't realize how deeply it influences our daily lives. Governments use it to plan cities, industries use it to optimize operations, and researchers use it to understand the world better. So what exactly is GIS? GIS is a technology that helps us create, manage, analyze, and also map data. It connects every piece of information to a location on the Earth's surface. Think of it as combining a spreadsheet with a map. A spreadsheet holds a lot of information, isn't it? Like maybe the population of a city, or the type of vegetation in an area, or the income level across neighborhoods. And a map will show where each of those things actually are. When you put the two together, that is the information and its geographic context, suddenly you will start seeing various patterns that start emerging, uh, which you could have otherwise not seen through that spreadsheet. Let me give you yet another example. If a public health researcher maps diseases across a city, GIS is able to reveal clusters that might be linked to poor sanitation or pollution. A forest manager, he can use GIS to see how trees cover uh, the land, or how the tree cover has changed over the years. Also, a disaster response team can identify which villages are most at risk from floods. And this is the power of GIS. It brings location intelligence into decision making. Now, GIS did not always look like this, right? In the early years, it was used mainly for digital mapping, essentially replacing paper maps with digital ones. But today, GIS has evolved into something far more powerful. It's a complete analytical platform that can handle both space as well as time, what we call spatial temporal analysis. This means we can map what is happening where, and also at the same time we can map when it is happening and how things will change over time. So when it comes to GIS, there are essentially three different kinds of functions that we deal with. One is a core function, where technology create, manage, and analyze the map, all types of data, um, where all the data is connected with respect to their geographical location and also descriptive attributes, which otherwise we would have saved in a table, and a table might not be able to give us a spatial intelligence. Here we used vector data, which represents uh, points or lines or polygons for precise spatial representation. Points could be something like maybe lighthouses, hospitals, could be any such feature that lies on the planet at a point. Lines, on the other hand, could be rivers or road networks or rail networks or the coastline. Polygons, on the other hand, speak of areas. Agricultural land is in it's an area. Forest cover, it's an area. Settlement, it's an area. Lake, or the shape of the lake or the area of the lake. The area is represented in terms of polygons, something that can be measured in terms of kilometers or meters, or length essentially will be represented in terms of lines. Then comes a raster data. The raster data is a gridded cell data where each cell holds attribute values, maybe elevation, maybe reflectance coming from that particular feature, or it could also be to do with temperature. So, GIS is the backbone of scientific research. It systematically will analyze spatial relationships and temporal dynamics, what we call spatio-temporal analysis of real world entities, because of which it serves as a unique problem solving technology. So what are the benefits of this? It improves communication efficiency. We will see it in more detail. It enhances management and decision making. And it also addresses humanity's greatest challenges. That is, if our data is present as a table, humans are not able to see patterns and paradigms in it. However, GIS allows us that imagination. It is critical for tackling climate change, sustainability, and social equity challenges inseparable from their geography. Now, this is why GIS has become such an important part of modern science and governance, that it allows us to model real world systems like ecosystems, cities, rivers, or transport networks. And it also helps us understand how they interact with one another. In short, GIS will help us ask better questions and find smarter answers. Now, the vision behind this GIS is deeply human. At its core, GIS supports our effort to understand and manage the complex spatial patterns that will define the life on Earth. From the spread of disease to the impact of climate change, from urban growth to resource management, every one of these issue has a geographic dimension, and that's where GIS comes in. So when we talk about benefits of GIS, we are really talking about four main things that we just discussed. It improves communication through maps and visualizations which speak for everybody. Anybody who looks at a map will be able to interpret it. So, better communication. It also enhances efficiency by managing and analyzing data in just one place. We need not categorize the data very religiously to be able to separately view it. All of it together we can integrate and we can find answers to the questions that we are trying to address. It supports better management such that it helps organizations allocate resources very wisely. And most importantly, it enables better decision making, which reveals spatial patterns that traditional data analysis often will miss. In today's session, we will do four things. First, we will trace the history and evolution of the GIS that we have just done, as to how it grew from simple map making to a global analytical framework. So, in 1962, the GIS was given birth by this Canadian geographer whose name was Dr. Roger Tomlinson, who introduced this concept and formulated Canadian Geographic Information System. That was the first operational GIS. You can see his photograph over here. Then there comes a transformation era. We will also talk about this in more detail. So, evolution of GIS is inextricably linked to advancement of information technology and data processing capabilities. Like most great technologies, GIS did not appear overnight. Its evolution is tightly connected to how computers and information technology themselves advanced over the past several decades, which means that along with evolution of computers and along with evolution of information technology, GIS has also evolved. So there was a time in 1960s, a time when computers were massive machines that filled entire rooms. Yet, even then, a few visionaries were already thinking about how these new machines could help us understand geography in new ways. One of those visionaries was Dr. Roger Tomlinson, often called, he's also called the father of GIS. In 1962, he introduced the idea of Geographic Information System while he was working on a land inventory project for the Canadian government. His work is the one that led to creation of Canadian Geographic Information System, which was the first operational GIS in the world. Now imagine uh, what that might have meant back then. Instead of working with piles of papers of maps, Dr. Tomlinson and his team were feeding data about land use, soils, and vegetation into computers and using those computers to create digital maps and analysis. That was revolutionary for its time. It laid the groundwork for every modern GIS system that now follows and now you see. This period, what we now call the first generation of GIS, they focused mostly on automating map making, taking traditional cartography and turning it into something computer could handle. A major milestone came in 1966 when Professor Howard Fisher at Howard University developed a software package to which he called SY maps or SI maps. It is short for mapping package. This was one of the first program that allowed users to generate computer based maps. Think of synapse as the ancestors of today's mapping tools. Simple by modern standards but groundbreaking when it was invented. And as technology improved, so did GIS, as we said, information technology with innovations in environmental technology, information system, sorry, and computers. GIS also evolved. So by the late 20th century, GIS entered its second generation, where GIS began to move beyond being just a technical mapping tool. It became a full fledged scientific system, one that could store, also analyze, and visualize very complex spatial data. Now, softwares became more modular and flexible, and researchers started using GIS to test their hypotheses or model processes and make predictions. In other words, GIS transformed from a tool that made maps to one that made sense to the other. So, the ones that were just maps to one now started making spatial sense to others who are weaving it. So now let's fast forward to today, and GIS has once again reinvented itself. We are now in what some call the third generation, a period of rapid transformation. That is, this transformation is essentially driven by advances in cloud computing, artificial intelligence, remote sensing, and there's an explosion of real-time data from coming from space mounted sensors and also mobile devices. We, you, me, everybody is a source of data. And it is really exciting. This evolution isn't only technological in a sense, but it is also systematic, which means that new theories will lead to better methods. Those methods will drive softwares, and the softwares will reshape entire industry. So, from a single researcher's experiment in the 1960s to today's global web based analytical programs, GIS has grown into one of the most influential scientific and decision support tools for our time, definitely. It's a story of innovating new technologies, innovating new methodologies which are persistent, and the humans will also desire to understand how our world really functions and how it changes through time. Now that we have seen how GIS evolved, let's also turn towards how exactly this data is made is put to work in GIS. A fully functional GIS is much more than just a piece of software. Like we talk about QGIS or ArcGIS, NV, we talk about so many softwares. So it's not just about a software, it goes a little beyond the softwares. It's a very complete system that will bring different hardware, softwares, data, also people, skilled people, and also different methodologies together. So it is it's a very conjugate system. All of them are working together in a harmony to process and interpret the information that is crucial for us to answer several questions. Let's look at each of these five components in simple terms. So there are five components of geographic information system. We'll just name them first. First is data, then there are softwares, hardwares, there are people, skilled people, and methods. The first one being data. Everything in GIS begins with data. If there is no data, there is absolutely no purpose. And where there is no purpose, there is no methodology. Where there is no methodology, there is absolutely nothing ahead of it as well. So data lies at the center. Everything in GIS begins with data. Think of it as a fuel that powers the entire system. Without data, GIS would be an empty shell. There are two major types of spatial data that we discussed in brief earlier: vector data and raster data. Vector data represents the world with precise shapes like points, lines, polygons. For example, a single point might represent a weather station. A line could represent a river or a road, and a polygon could represent a forest boundary or a city limit. On the other hand, raster data is made up of grids of cells, or what we call pixels. So when you take a picture of your friend and if you zoom in, it pixelates, it breaks out into pixels, isn't it? So these are called pixels. These are also called cells of a grid that are arranged in a grid, where each cell will contain some value. You can think of it as like a digital photograph of an earth, of the earth, where each pixel might represent maybe elevation or maybe temperature or vegetation density. So, in the past, GIS handled modest data sets, perhaps a few satellite images or a handful of shapefiles. But today, the scale of data has exploded vast. We are dealing with high resolution imageries from satellites and drones. Real time sensors also feed from the Internet of Things, that is IoT, and there's a vast stream of information that is available from 5G networks. So modern GIS isn't just about geometries anymore, it's about storing and analyzing space, time, and both of them together. So it is about where and what is available and when it is to be used and why it is to be used. So all these questions are answered by these data sets, by GIS using the data set. So data lies the most important component of GIS. The second is software, that is the engine that will drive GIS. uh, so if we talk about ArcGIS or QGIS or supermaps that provide the computational environment where all the analysis and visualization will happen. These platforms will let us overlay different data sets together, perform spatial analysis, or create 3D models, and even they are capable of simulating some changes over time, which means that definitely a skilled person will do it, which comes a little later. So whether you are studying urban sprawls, or you are tackling wildlife migration, or analyzing groundwater flow, or all these can be done in a GIS provided software, in a GIS software that provides you with the different analytical tools, so that you will be able to make sense out of the spatial data in a scientific manner, which is also visually interpretable. Then comes the hardware. This is the third component. It's a physical machinery behind all this software and the data set running. So in early days, GIS ran on large mainframe computers. Today, it operates on everything from powerful cloud servers to laptops and even mobile phones. The modern research grade GIS often relies on high performance computing, cloud infrastructure, and also GPU processing, which will handle massive data sets. Hardwares essentially will provide the muscles that will allow complex computations and real time processing to happen very efficiently. Now, the other thing that we were talking about, it's called people, and I will call it skilled people, because definitely, if somebody who doesn't have an understanding of data, or doesn't have an understanding of the concepts that are lying behind this data, or how to utilize a software, will definitely not be able to fit in this particular framework of five components of GIS, isn't it? So, skilled people. Um, even the most advanced GIS system is useless without these skilled users who know how to ask the right questions and interpret the results also correctly. Uh, these people could be geospatial analysts, or they are researchers, they are engineers, they're definitely students, not leave them behind, and also decision makers. All of them are decision makers because they are making decisions based on this data that is being processed and analyzed in the GIS, isn't it? So these are the people who will bring different domain knowledge along with them, and also critical thinking, um, that otherwise the software doesn't know. The software doesn't really understand the functioning of the environment, isn't it? It only understands how to produce your data on a map, and that is where the skilled person's knowledge base will come into picture. So GIS is a collaboration between humans and machines, where human have an intuition and machine computation come together along with this human computation to solve problems which are geographic, which have a geographic relevance. Then the fifth component is definitely method. If we do not have a methodology how to go about solving a particular answer, solving a particular question, that is a special query maybe, then definitely the answer will not be sorted, right? So the procedures or workflows and conceptual models that will guide a person or a skilled human as to how GIS is to be used, these are what is accounted for in methods. So these methods will include spatial analysis techniques, geocomputation, and interdisciplinary approaches that combine geography, statistics, computer science all together. When researchers use machine learning, for example, to predict flood zones or model urban heat islands, that's a GIS methodology in action. We have to have a formulated methodology that we have to execute in this GIS software using the data that is available along with us who are skilled to do this. And that is when we are able to come up with a structured way to convert this raw data into insights. So, definitely methods. So now that we have understood how GIS evolved and what its functions are, let us now talk about where the real GIS magic will happen. What we are going to discuss is applied research, its use, that is use of GIS in applied research. The role of GIS in research is to take questions that may seem vague or unstructured and turn them into clear or testable and evidence based models. We can also call it hypothesis, by the way. Mm, Think of it like this: if a researcher wonders why do floods occur more frequently in some regions, or if his question is how is vegetation changing across the Western Ghats through time, then GIS will help them translate these questions into spatial terms that can be measured, or they can be modeled, they can be analyzed. Different causal factors can also be understood. So, at its very core, GIS answers three types of spatial questions that we have to remember. Okay. So, first question is what is where? This is the most basic question. It often involves inventory making and mapping. For example, where are all the wetlands in a district? So, where exactly there are wetlands in a given district? So, that's a where kind of question that definitely GIS can answer. Then why is it there, why exactly it is there? So its association also comes into play. Now to answer this question, that is why these wetlands are there, we go a little deeper into the process and pattern analysis. And we also look for hidden relationship. For example, why there are certain areas more prone to landslides than others? Maybe they are steep, maybe the kind of soil that is available there is more susceptible to slippage, or maybe that this is the region where water is soaked by the soil and because of which it leads to collapse. So why a certain thing occurs where it occurs, this is a question that again GIS can answer. And GIS can also answer what if a certain situation happens or doesn't happen, what are the then what happens. So what if kind of questions also GIS is answering. So this is where exactly modeling and simulation will kick in to answer what if kind of questions, which will help us predict future scenarios. For example, what if urbanization continues at a current rate, how will it impact groundwater recharge? So these kind of questions which require a simulation can be modeled using GIS. Now, GIS will support two major kinds of analysis. One is exploratory spatial data analysis, what we call ESDA, and the other is confirmatory spatial data analysis, that we call CSDA. So, exploratory spatial data analysis is data driven. You use maps and spatial statistics to explore different patterns and to develop your hypothesis. For instance, noticing that temperature tends to rise within an urban expansion. And as you move in the suburb region where the amount of vegetation is more or agricultural land is more, there you will find the temperature is lower. So these are exploratory spatial data analysis. Then coming to confirmatory spatial data analysis, these are model driven. It involves building and testing models to verify your hypothesis that you have made in the exploratory spatial data analysis. And mm, also to verify these hypotheses repeatedly also you may verify. For example, if you want to predict flood risk based on elevation or rainfall and land use, then you are able to model the prediction. Now, because of this analytical strength, GIS essentially acts as a spatial decision support system, or SDSS. This is a tool that helps researchers and also decision makers to visualize the effects, or model the effects, model the phenomena, and evaluate these spatial data to make informed choices, data-based choices. Let us now look at where all we can use these uh, GIS across different domains. First is environmental and ecological sciences. So when it comes to environment, GIS is truly indispensable. It plays a very crucial role in conservation or habitat management or pollution control and overall sustainable development. So first, let's discuss conservation and wildlife management. GIS will be used to map habitats and understand how animals will move through landscapes. For instance, it can help predict where bears might cross highlands. Mm, this will allow planners to build wildlife corridors and reduce accidents. Similarly, GIS will also help track endangered species and also identify critical habitats. At the same time, monitor these invasive plant species also. The second one could be pollution and resource monitoring. um, so imagine trying to find out how industrial waste is affecting a river. For example, in a region there is this industrial waste that is affecting the quality of water in a river. The GIS can help pollution sources, can help us map pollution sources. Will also model how contaminants will spread downstream. At the same time, they will also identify those communities which are at risk, the ones which are constantly interacting with this polluted source of water are more at risk. The ones which are who are closer to this water source are more at risk, and then those which are away from it. So distance comes into picture. That again, GIS. Now it's also used to study air pollutions or urban heat islands that we discussed earlier, that in an urban region heat is high, whereas as you move in the outskirts, the urban heat island effect reduces. Then it also helps us understand water quality trends during the daytime, where the industrial effluents are constantly being released in the water system. Then the water quality is lower, water quality is reduced, whereas at night the water quality relatively improves. Or that in a certain season itself there are effluents that are coming into this particular river source, and that is why the quality degrades. Whereas during monsoon, when there is higher water discharge, then these pollutants get diluted. So these are the different scenarios that can be mapped and that can be understood through GIS. And the most popular, that is land use vegetation change, which is essentially done using satellite imageries. GIS will monitor these deforestation practices or agricultural expansion, or if it is urban sprawl. So, when it comes to India, for example, researchers will use what we call multi year Landsat datasets to detect how forest cover has changed seasonally or in a particular region. Seasonally, where temporal factor comes into picture, and regionally where geographic factor comes into picture. And this is very important for land management policies. Moving to the next one, that is earth sciences and climate change. Earth sciences will rely very heavily on GIS, um, and also remote sensing, that is remotely sensed data like that like that procured from satellites or from drones, that will help us in understanding how our planet is really functioning and how it is evolving. The first is geology and definitely resource exploration. Geologists will use GIS to map surface formations, also identify mineral deposits. They will also model subsurface water flows. For example, in mining sectors, will GIS will help us in optimizing exploration zones while also ensuring environmental compliance. Then oceanography and marine studies, GIS will help us see what is exactly invisible. That is, below the ocean surface that we otherwise is invisible to us. Then GIS will help us to see what is happening below the sea surface. It will map seafloor topography, if there is any coastal erosion or deposition, salinity changes, and also wave height. Uh, Coastal managers will use this data to assess flood risk, or they will also guide ships along safe navigation routes, identifying the bottom topography. Definitely, that's again based on GIS, because that is where location is important, precise location is important, maps are important. Then coming to meteorology and climate change, GIS will integrate massive amounts of climate data like temperature, precipitation, sea level or vegetation, um, which will detect trends and model future scenarios, how the temperature has been changing in the past and how is it likely to change in the future. Similarly with precipitation, similarly with sea levels, or similarly with vegetation. It will also allow us to visualize rising sea levels or melting glaciers or shifting ecosystems in such a way that simple graphs might not be able to help us in having a spatial understanding of it. So, in short, GIS helps us turn complex stories of climate change into spatial evidences that everyone can see and understand. Because maps, as we know, everybody can understand them and everybody can see them, right? Then, disaster management and public safety. Okay. So there are two types of disasters. One is natural and the other is man-made. And both of them, irrespective of whether they are man-made or natural, they have spatial dimensions. And GIS is very important in every phase, that is prevention, preparedness, response, and also recovery. In emergency planning, GIS will help us identify safe evacuation routes, plan relief logistics, through which ways logistics can be navigated, and also locate emergency shelters. In hazard assessment as well, it is used to map flood zones or fault lines or landslide prone areas, and also tackle tackle and track cyclones. After disasters, GIS will assist in damage assessment as well, or debris clearance, how to clear the debris. For example, there was a landslide on the road, then GIS will help us in managing that debris, where to dump it, in what manner we can excavate it such that the slope doesn't become unstable yet again. And also, it will help us in resource allocation. In criminal justice as well, GIS is used to identify hotspots of crime, such that police can optimize deployment. In epidemiology, for example, it tracks disease outbreaks, where exactly a disease first began, like that of maybe malaria, which will help us in identifying which are the hotspots, or maybe dengue. And it will also map these cases. At the same time, it will also identify which are the environmental factors that led to these hotspots. For example, if it is malaria, then breeding grounds of mosquitoes can also be identified. Then space research and astronomy, GIS can extend its reach beyond our planet. Space scientists use GIS principles to map celestial bodies and also analyze extraterrestrial landscapes. High resolution data from missions like that of Lunar Reconnaissance Orbiter or Mars rover, they are processed in GIS platforms to understand what are the surface compositions or the crater density and also tectonic structures. Then NASA's New Horizon missions, if you have heard of, to Pluto, for example, it relies on GIS based analysis to map terrain types and ice distribution on this planet Pluto. It's a dwarf planet Pluto. Then, looking ahead, researchers are even exploring the creation of universal celestial coordinate system. Like right now, we have only geographic coordinate system that is optimal for the planet, but then they are also planning for universal celestial coordinate system, which could serve as a GIS for space. It is a framework for future, that is in future how to explore the interplanetary routes. So GIS is a mapping tool. It is also a scientific bridge between data and discovery. So whether you are studying forests on the earth or craters on Mars, GIS is going to help you predict patterns or changes and also help you in making smarter decisions. Definitely always through uh, geography, that is space, and also place. Let's look ahead. GIS is standing at a very at a crossroad. It's no longer just a tool that we are using to map or analyze, but it is also evolving into a powerful intelligent ecosystem that is shaped by artificial intelligence, cloud computing, and also big data. All these, that is artificial intelligence, cloud computing, and big data, these are the forces that are redefining GIS, and what GIS can do, how it can operate, even how we think about geography itself. There are these new service modes like cloud GIS and geo AI. The first transformation is definitely the rise of cloud based GIS. So traditionally, GIS was something you installed on a single computer, like that of ArcGIS desktop or QGIS desktop. But today, that model is shifting to a cloud, which gives rise to what we call the third generation of GIS that we discussed in the previous, in the early minutes of this particular session. So in this cloud centric setup, platforms like that of WebGIS or Cloud GIS, and especially systems such as that of Google Earth Engine, if you have heard of this, they have changed the way researchers work. You no longer need a high end computer to handle huge satellite data. You can do it from your mobile phone itself. Everything that is from data storage to computation and also visualization, everything happens online. This means scientists anywhere in the world can collaborate in real time, analyze terabytes of spatial data, and publish their results very instantly. So the time gap between procurement of data, its analysis and communication has reduced, because of which yet again we have even more amount of data. The second major transformation is essentially coming from artificial intelligence. When we integrate artificial intelligence in GIS, which will lead to something called Geo AI. Now, Geo AI combines the pattern recognition power of AI with the spatial reasoning capabilities of GIS. It can detect features in satellite images, Also model urban growths or even predict social behaviors like that of traffic congestions. For example, imagine training a Geo AI model that has integrated GIS and artificial intelligence together to automatically identify flooded regions after a cyclone. Okay, using let's say sentinel imagery or Landsat imagery, it can process thousands of images within just minutes, a task that would take humans days or even weeks. So to that extent also we have reached. So globally, researchers are now developing domain specific large models like that of GeoGPT and Kunyon. You can search for these and read a little more about it. Intelligence systems, that these are intelligent systems, okay, the GeoGPT or Kunyon, intelligent systems that can understand spatial context, also terrain and geographic semantics, all of them together. These models are designed to think geographically, okay, which will enable machines to support scientific discoveries in ways that were once just impossible. To have humans are slightly slower when compared to machines, isn't it? Machines are also designed by humans only to make them faster. There's a pattern in which they go, and because of which the data recovery or scientific discovery is also rapid, which means that these models can think geographically along with a recognition of patterns, and also um, uh, they will support scientific discoveries. Now it's important to realize that simply increasing computing power or model size isn't enough. The real challenge isn't just processing more data, but it's also understanding the world better. So these machines should be able to not just process more data, but they should also be able to understand what phenomena are taking place, what are the changes that are taking place, and insights within the patterns that it has identified. That's where this advanced GIS triad comes in action. The triad that we are talking about is data, knowledge, and models. So, data is the raw material that is coming from satellites or sensors or drones or Internet of Things devices and social networks. It will provide observations that it has made about the world. So, you and I, all of us are data gatherers, isn't it? So, on your mobile phone, if there's a weather update coming saying that it is going to rain or it is raining, then you can correct that particular data saying that no, the weather app is telling me that it is raining, but it is actually not raining. So you are also a data provider, right? So that is to do with the data. Then comes the knowledge. Knowledge is what gives this data a meaning, um, that is captured through expert systems or ontologies, and that's now being called a geographic knowledge graph. Okay, it is now, this knowledge is being called geographic knowledge graph because that is where spatial context is also there, and information, that is data, is also there. And an understanding of these spatially varying data set, spatially varying data set is also there. That understanding itself is the knowledge. Then there are models. These are the tools we use to simulate or explain and also predict, whether they are physical models or water flow. So or statistical models where urban change is seen, or these are cognitive models of human behavior. That is also, by the way, done on GIS. So you might have heard of happiness index. A given country is more happier than as compared to another. So all these are again spatial data. Human behavior can also be produced on spatial data. When these three elements interact dynamically, they will form positive feedback loops. Okay. uh, data will inform models, models will refine knowledge, and knowledge helps us to collect better data. If we know in what way we have to collect the data, then definitely we will be able to feed in better data into these models, and then they will be able to make a better draw better knowledge out of this. So this cycle will represent the real intelligence of our future GIs. And it is not just automated computation, but also continuous learning and reasoning about the geographic world. The ultimate vision is pen spatial information system. We will talk a little about this as well. We also call it PIS. This is the grand vision of the future, where a GIS so where a GIS system is so comprehensive that it aims to describe and understand everything that exists in the space. So this pan spatial information system um, is a concept that seeks to build a unified framework that can handle data and also process across all possible scales. These scales could be macro scale, could be deep scale, or micro scale. Macro scale, when we talk about at the planetary level, it continues what GIS already does, monitoring earth systems, tackling land use change, climate, and material transfers across different continents, that is imports and exports. Also deep space, that extends GIS into the cosmos, mapping planetary bodies, analyzing asteroid trajectories, or building a universal celestial coordinate system to support deep space missions. And also micro scale, bringing spatial science down to the scale of the human body, where GIS principles could be applied in medicine. For example, a model organ system, or to study the spread of cells in biological tissues. Now, to achieve such a vision, we need a strong theoretical foundation, what scientists call information geography. And this emerging discipline will explore how geographic information is generated, transmitted, or transformed, and also applied. It's a bridge that connects our raw data, like that of satellite data, or any descriptive data that humans have collected, or machines, human developed machines have collected, everything together. And this science will ultimately make the PIS, that is pen special information system, possible. Now with this we will conclude, and mm, I will see you in the next session.